Hi everyone, I'm really sorry for the technical hitches there, just sorting out my computer. So sorry if I've kept you waiting for 10 minutes, but welcome to this Snap Revise revision session on GCSE physics efficiency. Just a reminder, if you've not joined us before, I'm David. I'm a GCSE and A-level physics teacher, and I've been doing that for probably about 19 years now. If you have any questions, please pop them up in the chat as we go, and I'll try and get to your questions as soon as I can. Every now and then I'll pause to just check understanding and make sure that everybody's happy. Please do take part. Please do talk to me if you feel I need to explain anything differently for you. So just a bit of information on online safety. Sometimes students forge friendships away from class on social media. And just to underline that these groups are not approved or run by Snap Revise. So if you do choose to link up on social media, please be cautious and make sure you limit your personal information on your profile. Check your privacy settings and make sure that your location isn't shared. And if you ever meet up in the real world, please tell people you trust where you're going, what you're doing, and ensure that it's at a public place at any time. I realize that students do use other services, but Snap Revise doesn't endorse or approve anything else. Thank you. So the objectives for today are to suggest ways of reducing energy losses in a transfer, understand what is meant by efficiency and how to calculate it, and thirdly, to explain how the efficiency of energy transfer can be improved, and that's a higher level topic there. We're not going to cover energy resources, but just identifying ways of reducing energy. We're going to finish off today by briefly discussing the improvement of efficiencies rather than just reducing energy losses, which is the higher tier content. In terms of the specification, AQA is usually the most detailed. So you need to be able to explain ways of reducing unwanted energy transfers, and you need to be able to use the efficiency equation. Of course, in this summer's exams, all equations are going to be given to you on an equation sheet or presented to you in the question. Only AQA students need to know about calculating efficiencies with powers instead of energies in joules. We won't be covering it in detail, but the calculation method is the same. Edexcel requires that you can explain ways of reducing excuse me, unwanted energy transfers, including through oiling, lubrication, and thermal insulation. Describe effects of thickness and thermal conductivity of walls of a building on its rate of cooling qualitatively, so without calculations, and to use the efficiency equation. And OCR, much the same there, just but slightly differently, but much the same as Edexcel. The bold spec point here is higher tier only, so describing ways to increase efficiency. So looking at methods of energy transfer, what are the three methods of energy transfer which we have here on the left-hand side of this slide? So the first one, second and third one down, what are the methods of energy transfer going on? If you'd like to pop a comment in the chat and let me know what you think. So what is the first type there, top left here? What's this one describing? Whoops, let's get back, excuse me. Pen on, so this first one here is describing a particular kind of energy transfer. Not seeing anything in the chat. Oh, there we go. Thank you. Samaya, heating. Yeah, brilliant. So that first one is heating, thermal energy transfer or heating. Yep, heat. Thank you to Chidinma. The second one's maybe not quite so obvious. We've got someone lifting something up. Yeah, so certainly we can have thermal energy transfer. It's actually a better word to use, but heating would be fine. Second one down here is a form of doing work. So this is doing work. We're doing work here by lifting up a box. And so we're doing work on the object because we're transferring energy into that system, the box and the person. So yeah, we're doing work against gravity, Thanya, thank you. Any work is defined as transfer of energy into or out of a system. In this case, yeah, kinetic energy to potential energy. Remember, work is force times distance, so the weight of the box times the distance it's being lifted up. And what kind of energy transfer is going on in the last example? The last example here, we've got a main socket. Yep, we've got electrical energy transfer. So it's energy transfer by electric current going on here. Thank you, Thanya, Simaya, Saba, and Chidinma, and Lahey Saint. Hi there. So dissipation of energy. What can we say about energy as a general rule, as a universal rule that we're taught? What can we do or not do to energy? And why do we use this phrase dissipation of energy rather than creation or destroying energy? Just looking at the comments in the chat there. Yes, electrical current is used to do work ultimately. Somalia has said it can be made or destroyed, and it can't be made or destroyed, only transferred. I think you mean that. Yeah, absolutely right. So it's never possible to create. So no energy can be created or destroyed. It can only be transferred to other forms, often less useful. And so we call that transference of energy to less useful forms the dissipation of energy. And that whole phrase would usually be something like the energy is dissipated to the surroundings. So in what ways and in what forms would the energy from the kettle example here on the bottom right, in what ways would energy be dissipated from the kettle? In other words, what are the non-useful transfers that we can't avoid? We're putting energy into the kettle. The kettle's putting energy into the water, which is the useful output. What are the ways in which the kettle is transferring out energy that's getting dissipated to the surroundings? What are the waste energies? Yeah, the kettle body itself heats up. So we're going to get heat loss from the surroundings, perhaps out of the spout of the kettle as well. There'll be energy lost in heating up the body of the kettle. Yeah, there could be a little light in the kettle there, which might be something that's a wasted energy in terms of the useful output of the kettle. And there's also going to be sound. Thank you, Somalia. So the sound of the kettle boiling, sound energy there is going to be dissipated to the surroundings as well. So the two major ones here in terms of energy per second of power are going to be the heat loss and perhaps the sound second, and then light. So the principle of energy conservation states that no energy can be created or destroyed, only transferred from one form to another. So total energy input into a system is equal to the total energy output from that system. But the energy can be transformed or transferred to multiple different forms. And as we've discovered, some of them are not useful. Okay, let's look at reducing energy losses. So methods of reducing energy losses. So the first thing, when two surfaces rub against each other, we might have some kind of mechanical machine, and we've got surfaces that are potentially going to rub against each other. What can we do to reduce energy losses there? What happens when two surfaces rub against each other? Yep, thank you, Thanya. So we're going to get friction. So we're going to get heat build up. Due to friction. And how can we reduce the energy losses? Well, we can use lubrication. So some kind of fluid, could be water, could be an oil, could be grease, can reduce energy losses. And that basically by reducing frictional forces. So it can make, in this case, the gears, it can make them easier to turn. Again, your choice of lubricant is going to depend on the situation. In space where you've got mechanical parts that need to open and close in really freezing conditions, but many, many degrees below the freezing point of water, sometimes they use a powdered lubricant. You don't need to know detail, just something, usually an oil or a liquid though, which can make objects slide more easily past each other. And what will a warm object do to lose energy? So another method of energy loss from something that is warm, where is energy going to go from a warm object? Yeah, thank you, Dee. So a warm object will lose energy as it emits heat to the surroundings. Okay, good. Thank you, Samaya and Tanya as well. So how does thermal insulation help? Thermal insulation can reduce energy losses by doing what to reduce this emission of heat to the surroundings? What kinds of things does thermal insulation do to minimize that unwanted transfer? Fundamentally, all thermal insulation works to reduce heat loss to the surroundings. And I'm just looking in the chat, we've got traps thermal energy, so it's harder to escape, reduces the amount of thermal energy being sent to the environment. Of those 2 points in the chat, Somalia and Thanya, I think, and Dee is correct there, I think the comment from Thanya and Dee are probably slightly better worded in the scientific sense. I do get students sometimes saying that insulation traps heat. And technically insulation isn't doing that, it's trapping air or preventing a low conductivity barrier between something that's hot and something that's cold. So I try and avoid saying traps heat, but certainly you can say reduces thermal energy transfer, and it will increase the temperature difference between one side of the insulation and the other, so that's correct too. Essentially, insulation helps to keep the heat energy on the side of the insulation that we want to keep it on. So insulation helps to keep heat energy in, or indeed out. If you want to remain cool on a hot day, you want your insulation to do the same in the other way. Okay, brilliant. So when we do work on a surface, we get friction. That energy to be put in as the work being done makes the surfaces heat up due to little tiny imperfections on the surfaces as they slide over each other. And if we put lubrication in between the surfaces, we move them just a tiny bit further apart so those imperfections don't catch as much. And that's what makes the surface have less friction and less heat buildup due to friction. Okay, let's look at heat loss in buildings. So the rate at which the inside of a building cools can be reduced in a number of methods, or by a number of methods, and you need to know how to describe the ways that heat is kept inside a building, such as in a house on a cold night. So what kinds of ideas do we have? What can we do to this house here to add to its insulation and reduce heat loss from the building? So thank you, Dover there, we've got D as well. So we've got all the good ideas there. Loft insulation, draft excluders, double glazed windows, cavity wall insulation. Yeah. And the type of bricks used, yeah, lots of bricks have air trapped within them as well, or even foam inside them to prevent or rather reduce energy loss through heat transfer. So we are going to use thermal insulation in the walls. We could make the walls thicker. Very thick walled buildings tend to have more constant temperatures because it takes longer for heat to transfer through it. So we can make the walls thicker. And we could add double glazing. Which gives any heat 2 layers of glass through which the thermal energy needs to be conducted. So that takes longer. And often double glazing has a low conductivity gas, which is trapped between the glass. So that reduces convection as well between the 2 pieces of glass. So that's how double glazing helps. Yeah, thick curtains, carpets. Also good ideas. We've got loft insulation that's been mentioned. That could be foam or fiberglass. We've mentioned double glazed windows. Thick walls, and cavity wall insulation was mentioned. So cavity insulation in the walls. Anything which essentially is going to trap air, reduce the movement of air, particularly convection, and also anything that's going to reduce conduction is going to increase the thermal efficiency of a house and reduce the heat loss. Okay, how's that so far? So we've covered essentially what transfers of energy take place, how we call those transfers non-useful if they're transfers which are dissipated to the surroundings rather than useful transfers. We've covered that doing work on a system puts energy into it, and that we can try and keep as much of that energy there if it's thermal energy by insulating the system. So if you could give me some 1s, 2s or 3s over in the chat, that would be really good. Hopefully you're all on a straightforward. And if you've got any questions, as I say, please do pop them in the chat. Cool, thank you, Dee. Thanks, Jaqueen. Dover, excellent. 1 so far. Don't be scared. If you've got a 2 or a 3, I'm more than happy to re-explain anything that you'd like me to. Thania, thank you. Okay, I'll keep my eye down on the chat there, and if I see any 2s or 3s come up, you're welcome to expand on what you'd like me to cover further. Let's have a look at an example question. Oh, I've got a 3 from Marcia there. Marcia, do you have a question for me? How can I explain better for you any of the ideas that I've covered? Is there anything in particular, Marcia, that you'd like me to go through again? Thanks, Lahey. Just give Marcia a moment. But if anything comes to you later, Marcia, and there's anything that's confusing you particularly, then please do let me know. One thing I'll add is that heat always travels along a gradient. It'll always travel from a place where there is a higher thermal energy to a place with a lower thermal energy. So something hot to something cold. So heat will always try and move to even out the temperature between 2 places until those temperatures are the same. And so by using insulation in between 2 areas, which are at 2 different temperatures, we're actually slowing down that transfer and keeping the gradient steeper, if you like. We're keeping the hotter side hotter for longer by slowing down the transfer of heat energy through a barrier. Okay, I'll move on to an example question that asked Amalia here. I was wondering if you're going to go through conduction and convection. I may mention it, and if I have time, I can touch on it in explanation today. It's not specifically part of what we're doing today, which is efficiency, but if we have time at the end, Somalia certainly can do that for you. So bring it up again if I've forgotten when it comes to the question section at the end. Let's have a look at a typical question here. This is an OCR question. It's a foundation level question. I'll read through this and we'll think about the answers. So a householder heats water with an electric heater. The water is then stored in a large storage tank until it's needed. If the water is not used for some hours, it will cool down and the electric heater must be put on again. Suggest and explain one way in which the householder can reduce the energy wasted in this way and so save money on the electrical bills. These are topics which will come up in the exam. Thank you, Marcia. If you want to clarify for yourself, I could spend an hour talking about what's been excluded from some of these exams on its own. If you go to your exam board's website, AQA, Edexcel or OCR, or if you're doing international GCSEs, the provider for those, you will find an announcement regarding this summer's exams. And it's relatively easy to find on the specification page, and there's a document there which will tell you which topics have been excluded. And they also tell you which topics are going to be focused on in each of the papers for physics, chemistry and biology. Chemistry, I know, has had very little excluded. Physics has had a bit more excluded. So Marcia, that's your best bet there, to just put your mind at rest, and you can go through your revision guide then, and with the correct specification update in front of you, you can literally cross out some of the bits you don't need to worry about now. So just looking at this question, I've got some good answers coming up here. So lag the hot water tank. So we could lag the tank. I think it probably needs a little bit more information, because we probably need to explain what lag is. So lag the tank with thermal insulation, I'm going to say. Again, that's going to slow down that heat transfer from the hot water in the tank to the outsides, which are cooler. Why would we lag the tank? I'm going to assume this is a 2-marker question, so we need to say a couple of things. We've said what we'll do, but why will we do it? Why is lagging it going to help? Something nice and simple. Just looking at there, by using it as a storage tank, I'll come to that. Wrap it in something that doesn't conduct thermal energy. Everything can conduct thermal energy. Some things very, very tiny amounts. But lagging it will slow down thermal transfer out of the water. I can see we've got quite a few questions coming up, and I'll address those now. So maybe wrap it in something that doesn't conduct thermal energy. Yeah, the best material, I mean, there's a limit to what makes sense, because obviously you could wrap it in a meter of foam, but then you'd have a very large hot water tank. So there's a balance to be had. A storage tank surrounded by insulation, which would reduce it. Yeah, some tanks come naturally now, already wrapped thickly in foam. Could you explain what lag means? So lag, in this sense, lagging the tank, that's why I explained it. You could effectively replace that word with wrap. Wrap the tank with thermal insulation. Lagging is an English or Anglo-American word which refers to a jacket that's put around something as insulation. So just saying wrap the tank with thermal insulation is great. You don't need to worry about the word lag. And yeah, the trapped air in that layer of thermal insulation is what's going to help keep the heat in. It's a really poor thermal conductor. Yeah, putting a polystyrene top on it too, even, you know, the things you don't need to worry about, you could go into more detail if you wanted to be a plumber in later life, but basically cover it in insulation, and that will slow down the heat transfer. Yeah, you could do, Marcia. You could heat the water quicker and just on demand as well, which some systems do. So valid, but a lot of the time, particularly with foundation level questions, it's straightforward, almost, I would say, common sense answers that demonstrate your knowledge of physics and physics words, correct words, so thermal insulation, transfers, and so on. Okay, so let's move on to part 2 now and talk about efficiency and the efficiency of a system. So efficiency is a kind of a measure of how much energy is usefully put to work in a system compared to the total energy that you put into a system. So efficiency is the proportion of useful energy from a transfer to the total input energy. So in the case of the kettle here, Yeah, so it's efficiency is a way of measuring how much energy is being lost. Generally speaking, if you want to save energy and therefore money, then you want to get your efficiency as high as possible. I can see Dave is saying, yeah, energy transferred efficiently, 80% wouldn't be too bad in some cases. And Lahey there's got efficiency percentages, the useful energy out divided by the total energy in, and then you multiply the outcome of that by 100 to get a percentage. Yep, useful energy transferred, total energy supplied. Thank you, Tanya, that's great, all correct. So in the case of our kettle here, we've got 500 joules of electrical energy going in. So that's our input transferred into it. And then we've got some useful energy coming out. The useful energy is going to be the heat of the water. So that is useful. And then we're going to have some wasted, we'll have some wasted sound and heat through the body. And in this case, that's totaling 100. So in our kettle here, our example here, we've got 400 joules usefully transferred into the water in the kettle, but 100 joules is being wasted. So we can calculate the efficiency of our kettle by looking at the total useful out divided by the total energy in. In this case, that would be 4/5, wouldn't it? This would be, in fact, 80% efficient, as someone's already said there. Thank you. So in general terms, efficiency is a unitless number because we are always dividing energy by energy, or in some cases, power by power. So it's unitless. It'll give you an integer less than 1 or between 0 and 1. But if you multiply by 100, it'll give you a percentage. So just small point to note, just check your questions asking for a percentage if it is. Sometimes they do, sometimes they just ask you for an efficiency, in which case you could just give your efficiency as 0.8 in this example here. But if it asks for calculate the percentage efficiency, you need to remember to multiply 0.8 by 100, and that will be 80%. So efficiency is useful energy output. And we'll talk about energy, so that's going to be in joules, the useful output. We're going to divide that by the total energy input. And that's also going to be in joules, hence the unitless nature of efficiency. And we can, as I said, calculate these using powers as well, provided you use power on top and bottom. But most of you will only need to be dealing with joules. Okay, I think I've covered everything here. Are there any questions? I can see from the chat that you're fully on board with how we do this calculation, and Dover got there straight away with the 80%. And then several of you have quoted the equation and done the calculation for me there. Hey, thank you. So if you're happy, Marcia, are you okay with this? Are you happy with this idea? So efficiency is useful out over total in, and you're always going to expect a number between 0 and 1. If you get a number bigger than 1, you've probably done the calculation upside down, almost certainly. So you can do a little logical check on your answer. Okay, let's look at another efficiency example. An AU, I don't think I mentioned AUs. If I did, I didn't mean to. But an AU usually refers to an astronomical unit, which is the distance between the Earth and the Sun. So, but not something we're talking about today. Okay, so let's look at the efficiency example of a car engine. A car engine is filled with fuel containing 5 kilojoules of energy. And as the engine runs, 500 joules of the energy is lost as heat and 300 joules is lost as sound. The rest is converted to kinetic energy, which is, of course, our useful output from an engine. Oh, an arbitrary unit. Sorry, it's similar. Yeah, we don't give efficiency an arbitrary unit at all, perhaps other than the percentage sign. So joules over joules is 1, of course. So we just state it as a number, as a ratio. So the efficiency example here of a car engine, we're calculating the efficiency of the engine. So the efficiency is going to be equal to the total useful output. So we need to calculate that. Just go back a step. So useful output is going to be equal to 5 kilojoules, which is 5,000 joules, minus 500 lost as heat and minus 300 lost as sound. So that's going to be 4,200 joules. That's our useful output energy. So our efficiency is useful output divided by total input, both of these being energies. So I'll just put the J there to make that clear. And that's going to be equal to 4,200 divided by 5,000, the total amount of energy we put in. And that works out at 0.84. And in many questions on efficiency, that would be fine for your answer. If you want to turn it into a percentage, then we multiply it by 100, and that's going to give us 84%. So that is a remarkably efficient car engine, to be honest. I believe that most petrol car engines are much lower efficiency than that. They're down in the 20s and 30s. Is everyone happy with the way that I've taken the numbers from that example and thought about how to work out the useful output from those numbers given, and then worked out the efficiency by putting the useful output over the total input? And I do find it's always quite handy just to underline key information when you're looking through a question like numbers, and also calculate, explain, state those command words. It gives you an idea of what the examiner is expecting. They're expecting to see a calculation here. If you just wrote down a correct answer, having typed it all into your calculator, you'd probably get 4 marks, but you could lose a mark if you make an error and the examiner has no example of your thinking and your working to look at. So always best to show all your working, even if you think the question is simple to do without doing any writing. Okay, let's move on and talk about improving efficiency. So there's 2 ways we can improve the efficiency of a system, a machine, a device, anything you like. 2 things we can do to fundamentally improve its efficiency. We can reduce 2 things. So we can first reduce the energy losses. And in terms of thermal energy efficiency and thermal efficiency, we do that by making it harder for heat energy to travel from one side of the insulation to the other. We slow that transfer down, and we can reduce energy losses in other ways by better design. In many different cases, mechanical and electrical, we can improve energy losses, often by reducing energy dissipated as heat. So the examples here for energy losses are going to be the one we just mentioned. So thermal insulation, that's going to reduce thermal losses. Lubrication to reduce frictional losses. Two key ones spoken about so far. And in terms particularly of this example of a car, we've also got streamlining or aerodynamics. Either word be fine. So streamlining means designing a shape that's designed to move through a fluid like water or air, designing that shape to be able to do so in a more slippery fashion. So we make the object narrower, more pointy. We reduce the turbulent flow of the fluid afterwards, but just essentially streamlining, making something more streamlined. Think of a Formula 1 car versus a double-decker bus. So there are key ways there of reducing energy losses. We can also reduce energy, we can also improve efficiency by reducing the input energy to a device. Of course, if we can reduce the input energy for the same outcomes, then we're going to get a higher efficiency because we're going to get more percentage of useful energy out with respect to what we put in. So we've got an example here of a forklift. So if it needs to lift a weight as well as its own weight and a load, they're actually placing their own weight on the ground rather than the whole forklift going up. So in this idea, we've got a load that goes up. Let me try and explain that. So in the forklift, only the forks doing the lifting move up and down. So most of the weight of the forklift is staying put. So you're not putting energy into that system to move or raise the most weight of the forklift itself. And we can also use cranes. So if we're moving building materials, we can use cranes, and they have pulleys. So with pulleys and also counterweights. They will also help to reduce the input energy. If you're trying to raise something up, if you can allow something else to come down naturally using gravitational force, then so long as that thing you're sending down is a little bit heavier than the thing you're sending up, you can do so with very little energy. And actually, that's how some railways work on seaside resorts, where you've got a flow of water like a river. They fill up tanks with water as a counterweight to balance the weight of the people getting on at the bottom. And when the tank is full enough, it becomes just heavy enough for gravity to pull the water down and lift the people up. And then once the people arrive, the tank can be emptied and the top station loaded with people. Well, not emptied because the people will come down very, very fast, but some of the water reduced, and it can go up and down like that with minimal input energy, just using a natural resource. Obviously, that kind of detail is not going to be expected of you in an exam, just ideas that you can reduce energy losses, friction, insulation, and that you could also design something so that the energy it needs to do the job is actually less, using pulleys, efficiencies of pulleys, counterweights, and only having minimal moving parts. Right, I've talked quite a lot on that one. It's been a bit quiet in the chat, so I'm just going to ask if there's any questions on that so far. And if you'd like to give me some 1s, 2s, or 3s to let me know how you're feeling on that. Are you happy with the idea that we can improve efficiency by either reducing input energy, total input energy, or reducing energy losses? And both those things work directly in the efficiency equation to give you a number closer to 1. Thanks, Lahey. Yeah, so anything you can do that will bring your efficiency calculation closer to 1. In theory, I guess nothing would be 1 efficiency 100%, because there tend always to be some kinds of losses. I was waiting for a few more numbers from people to come up to show me how confident they are. Thanks, Samaya. I think one of the most efficient things that you've probably heard talked about is an electric motor. Electric motors are very highly developed. Part about a crane, yeah, by all means. So if we have a crane, sometimes a crane can operate. I'll draw a little picture. Excuse my picture. There we go. So we've got a crane here, and we want to lift a really big load here. We want that to come up. Now, cranes have counterweights for 2 reasons. One is to balance the load along the top of the crane's beam, so the counterweights can move forwards and backwards. And sometimes cranes have a counterweight that can fall. So the counterweight can go down, and when it goes down, the load can lift up. And there's our counterweight. And there's only a little bit of assistance required from an electrical motor, so electrical energy put in order to assist the process. Whereas if you had no counterweight that could go down, then you're going to use all electrical energy input to lift the load. Of course, that system is only going to work if you've got something else on the load side you can then lower down again. So this isn't always applied, but my example of a funicular railway on a cliffside using water and people as movable counterweights is another good one. I wouldn't get too bogged down in that one, though. I would just state in terms of reducing energy input by designing fewer moving parts, making sure you're not lifting parts unnecessarily, and in terms of reducing energy losses, you're insulating, you're using oil or other lubricants in order to reduce friction. I can't see an example of a crane coming up. It's going to be a bit too complicated to explain. Okay, let's have a look at another couple of exam questions. So here we've got an example from Edexcel. This is a higher level Edexcel question from the old spec. Some students investigate the efficiency of electric motors. The students find that one electric motor has an efficiency of 60%. Explain in terms of energy what is meant by an efficiency of 60%. Thanks, Tanya. I hope that was of some help. And yeah, it's nice to see that it helped you. So they found an electric motor has an efficiency of 60%. Explain in terms of energy what's meant. So you need to say that 60. Would one of you like to have a go in the chat before I write any more, to be fair? Otherwise, I feel I'm just writing the answer. I know there's a bit of a delay, so I need to bite my tongue and give you a chance to have a think. So it's a 2-mark answer required. So we're going to use a number. It makes sense to use the number that's given in the question. It might be good to quote the equation, Lahey. Yeah. We're not going to write an essay here, but a couple of good points about what that 60% efficiency means. So I'd probably combine what I was about to write here with what Lahey has said there. So 60% efficiency yes, Samaya, indeed, yeah. So 60% efficiency means 60% of the total it's an electric motor, so I'm going to mention electrical energy. 60% of the total electrical energy input is transferred into what's the useful energy output of a motor? So we're going to transfer 60% of the total electrical energy into useful, sort of primary function of a motor is to make things move. So we're going to say useful kinetic energy. Oops, there's an E in there. Sorry, I'll write that again. I'll find the rubber feature on here where I want it. Right, okay, useful kinetic energy. There we go. And that would be enough. We've talked about 60%. We talked about total in. 60% of the total in gets transferred as useful kinetic. You could add something else, but there's nothing else we need to add. We could write the equation. You could say 40% of the input energy is, I would say, dissipated. Never say lost. And you could add dissipated, excuse me, you could add dissipated into the surroundings, but dissipated is fine. Never say 40% of the energy is lost. And I'd even try and say, avoid saying lost to the surroundings. I'd just say transferred, not without use, transferred less usefully to the surroundings, but dissipated says it all. And looking at what Tanya said, it's a percentage which shows the amount of energy which is useful over the total energy. Yeah. That's right, if you multiply your answer by 100 to get a percentage. So we're all happy with that one for 2 marks, I hope so. Catch me up with a comment or a question in the chat if you're not. Wasted, yeah, I think, yes, Samaya, you can say wasted. Wasted into the surroundings. I'd always try and get the idea that it goes somewhere. But you could say wasted to the surroundings, anything like that. Dissipated into the surroundings is probably the premium phrase, if you can remember that. But yeah, as long as it's understandable what you mean, as long as you don't say lost or gets lost or is disappeared magically, because we can't do that with energy. Let's have a look at another example question. So here we've got a train powered by a diesel engine. The diesel engine is used to turn a generator, and the generator provides electricity for electric motors which drive the wheels. So we've got an engine spinning a generator, producing electrical current, providing energy to the motors at the wheels. And then under that, we have a diagram which represents the energy transfer in 1 second in the generator. So in 1 second, we've got these energy flows going on. We've got 1,400 kilojoules being placed into the system. And the useful energy output from that, which is converted into kinetic energy in the electric motors, is 1,300 kilojoules. And then we've got an arrow from our diagram here pointing downwards, which says energy wasted, but no number. So without reading the questions, we're likely going to be asked what that amount is. And this arrow diagram is often called a Sankey diagram. A Sankey diagram is a word that many teachers use, may come up. That just means an arrow diagram showing energy flow. We normally show energy wasted as an arrow going down. So question 1, calculate the amount of energy wasted in 1 second in the generator, where we've got 1,400 in, 1,300 useful out. So the energy wasted must be the difference between the two. And Tanya's gone ahead and done the calculation. Brilliant. We'll go through that in a second. So we've got 100 kilojoules there, haven't we, which is the wasted energy. And then the calculation is for the efficiency. So the efficiency is going to be equal to the useful output energy, which is what the electric motors are putting out. Useful output energy divided by the total in. And that is going to be 1,300 divided by 1,400, which equals 0.93, which is exactly what Fanny has got there. I'd almost certainly always round these to two significant figures. And it doesn't say calculate the percentage, so 0.93 would be a perfectly good answer. If you wrote the answer as 93% in this case, you would also get full marks. Excellent. So for 1, do you leave the answer in kilojoules? It doesn't matter. If you converted it into joules, that would be fine. But it's just longhand. If you do that, you could write 100,000 joules. Just be careful. If everything's in kilojoules, I'd be tempted to leave everything in kilojoules because it means you're less likely to make an error in a calculation. Because so long as they're all scaled by the same factor, it won't affect your percentage calculation. So there's no advantage in expanding these out into joules. But watch out for that, just in case one of these numbers could have been placed in joules to make you have to think a little harder. I don't think examiners are generally that mean, but just in case. Okay, let's have a look at a final example question, and then if you've got some questions on convection and radiation, come back to that for a few minutes. I did start a little bit late, again my apologies for that, so I'm quite happy to move on a little longer. If you have another SnapRevise session to go to, though, I realise that might overrun, so you might wish to go to it if there's one scheduled. So this picture shows a radiator which is being used to heat a room of a house. We've got water entering the radiator here, and we've got water leaving the radiator over here. It's full of water which flows from a boiler through the radiator and back to the boiler. So we have this circuit. The main boiler can be replaced to improve efficiency. Describe 3 ways, excuse me, that the efficiency of the pipe system can be improved. So we've got all these pipes in this boiler system. What 3 ways could we improve the efficiency of the pipes in this boiler? Well, much like a tank of hot water, we could wrap the pipes in thermal insulator. Thermal insulating material. I'm just going to say wrap them in thermal insulator. We could reduce the length of the pipes as much as possible, according to the dimensions of our house, of course, but we could reduce the length of the pipes, and that would lower the time that the heat has to transfer across the pipe wall, reduce the length of the pipes. And another thing we can do is we can reduce the radius of the pipes. And if we reduce the radius of the pipes, that's going to give them a smaller surface area, which will therefore mean less heat can be radiated and lost into the surroundings or by contact conducted into the surroundings from the pipes. So we can wrap the pipes in insulation, we can reduce their length, or we could make the pipes narrower, reduce the radius, and give them a smaller surface area. Yeah, they're the key ideas it's looking for you to come up with here with these 3 different types. Yeah, making sure the pipes are clean and smooth improves flow efficiency, but actually that would have more complicated upstream effects on efficiency. You're not wrong, Thanya. That would probably increase power consumption of the pump pushing the water around rather than reduce the thermal losses due to the water in the pipes. But we want the water to be clean. We don't want any obstructions. One of the problems of thinner pipes is they can get clogged up with minerals and limescale. So there are trade-offs. But yeah, we're getting into a bit too deep a conversation. They're the 3 that you need to know for this one. Okay, so we've covered the main objectives to suggest ways of reducing energy losses in a transfer, talking about insulation, lubrication, and then later surface area. Hopefully we will understand what's meant by efficiency and how we can calculate it. And for those of us doing the higher paper, we can explain how the efficiency of an energy transfer can be improved. And those last 2 questions were on those bases. So questions you had for me. There were 2 earlier that came up. Radiation is a form of heat transfer by EM waves, electromagnetic waves, in particular infrared. So radiation is always an electromagnetic wave given off in an infrared spectrum, and it radiates in all directions, and anything that is hot, any hot body, always gives off radiation in the form of electromagnetic infrared waves. The only time it wouldn't if it was cooled down to absolute 0, something like minus 273 degrees. So that's why infrared radiation, being a wave, an electromagnetic wave, travels from the sun to the planets of the solar system and warms our atmosphere and our oceans and our land. Infrared waves, being radiation of electromagnetic waves, don't require particles. Okay, so this is how heat is radiated. Radiation meaning giving out in all directions, and no particles are needed for that kind of heat transfer. Whereas when we have convection, convection is effectively when we have a body of a fluid within a larger body of fluid, if you like. So you can imagine an area of water in a beaker. If we heat this fluid here, could be a bit of air. If we heat that fluid, then the fluid will expand. The molecules won't expand, but the volume will expand and it will rise up. And when that little bit of heated fluid gets to a higher position, it will probably cool down again when it's away from the source of heat. So it will shrink and it will sink. And that's called a convection current. And that's what drives energy flow in our oceans and in the atmosphere. And in a very simple term, if you have a hot air balloon, there we go, there's a hot air balloon. If we heat up the air here, and then the balloon will expand slightly, and the whole balloon will rise up in the atmosphere because it's less dense than the surrounding atmosphere. So I hope that's a bit of a potted explanation of convection, worth looking up in your revision guide, should be nice and clear in there, and a potted explanation of radiation. Conduction is where you have a solid, very little conduction occurs in a liquid, and in a solid where you have conduction, you have particles that are against each other. And those particles, if we heat one end of a solid rod, so if we add some heat here, then these particles begin to jiggle around a bit more. They just vibrate about fixed positions, and those vibrations are passed on to the molecules adjacent to them until eventually the heat flow travels along the rod. And if it was a metal, you'd also have little electrons there whizzing around freely, and they increase the conductivity of a metal. And that's why metals are very good conductors of heat as well as electricity. So I hope that covers very briefly the three kinds of heat transfer for you, if you had any questions on those. Yeah, so in metals and non-metals or plastic, as I just said, conduction in a solid that isn't a metal just relies upon the vibration of particles about fixed points. Yeah, and in a metal, it's electrons that are freely able to move. Metals always form ions, positive ions in a lattice structure, and they give up electrons which are free to move around. Okay, thanks, Somalia. So is that Somalia or Samaya? It is Samaya. I was getting it right. And I hope you all have a great day as well. And I hope that was of use. And I look forward to seeing you in a future session. Let's have a quick look. And upcoming web classes, we've got a maths web class on the 20th of March. So your next upcoming web class on the 20th of March. And I wish you all a good day and a good evening. And thanks very much for coming. Bye-bye.